Okay, in 7b we're talking about combining probabilities. We'll have two major ways to combine events, and then we'll calculate the probabilities of those events. And one way to combine two events is with the word and another way is to combine two events is with the word or. So we'll see both of these situations in these notes, and we'll end 7b talking about at least once probabilities. So to start with and, we're going to look at formula right here. So we have two events, A and B. If these two events are independent, we'll see what that means in just a moment. If these two events are independent, then the probability of A and B is equal to the probability of A times the probability of B. So it's and will always tell us to multiply the probabilities together of each of the two events if the two events are independent. If they're not independent, we'll have to be a little bit more careful. Well, what does it mean for two events to be independent? Well, it means that that one occurring does not affect the probability of the other one occurring. So if the occurrence of either of them has no effect on the probability of the other one. So that's what independent events are. So this will be more clear as we look at the examples. And dependent events we'll see in a couple pages. So to start, the example tells us we're going to toss a fair coin 6 times. Now we're asked to find the probability that all 6 tosses result in heads. Okay, so the key word here is all. And probability questions can be a little bit tricky because they might not say the word and every time. But in order for us to satisfy the event, all 6 tosses result in heads. That means the first has to be heads, and the second has to be heads, and the third. So let's go ahead and start our probability calculation. So the probability that we land heads, 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 6 heads in a row. Well, to give ourselves a little clue here, it's not a necessary step, but it's nice to see how this is an and situation. For this to occur, the first needs to be heads, and the second one needs to be heads, and the third needs to be heads, and they all need to be heads for all 6 to be heads. It's clear from saying the same thing essentially, but using the word and, it lets us see what formula might be useful. Now each one of these H's representing heads is an event. So it's heads on the first toss, heads on the second toss, all the way through to the 6th toss. So we can split that up as an and probability. I'll do that first, and then I'll always go back and check and say, okay, do I need to be careful about whether or not these events are independent? So finish writing out 6 of these. Probability of heads. So question of whether or not heads is one toss is independent of the next. Well, that kind of says it all. Yeah, the first toss has no influence on the second toss, and the second toss has no influence on the third. If we land heads on the 4th, it doesn't have any implication. It doesn't affect the probability at all of landing heads on the 5th toss. Okay, so these are independent events because no event affects another event's probability. So now we just have to look at what the probability of landing heads on a single toss is. Well, on a fair coin, that's 1/2. We're tossing a fair coin, so that is 1/2 times 1/2 times 1/2, all the way 6 of these, or 1/2 to the 6th power, and that number is 1 over 64. So we have 1 over 64 as our final answer in this one. So that's the probability of landing heads 6 times in a row on a toss. Now, another and probability question. We have a roulette wheel. A roulette wheel has 38 numbered slots, each of which has an equal probability of the ball landing in it. The slots are partitioned into 18 red, 18 black, and 2 green. What is the probability of red occurring for each spin and 3 consecutive spins? So very similar to the last one. We're asking, what's the probability that we get red, red, and red? I just said and. That's nice. In 3 consecutive spins, it's red every single time, no exceptions. So we can say red and red and red. Okay, so we link these with an and. We realize we have an and within our probability. So our events are linked by and we know that we'll multiply this every time. Multiply the probability of red times the probability of red. Now, whether or not the events are independent or dependent, we're always going to use a product. It's just for dependent events later, we'll see we have to adjust things. So here we are, probability of landing red times itself 3 times. Now, what's the probability that we land in red with the roulette wheel? Right, remember the roulette wheel with its 38 numbered slots? The wheel is spun, a ball is dropped into the wheel, and it lands randomly in any of the 38 slots. To play it again, we pull the ball out, spin it, drop the ball back in. So there are 18 red slots. 18 red slots. So that's 18 outcomes satisfying the event of red divided by 38 total slots. So 18 divided by 38 is the probability of landing red in a single spin. So that's the case for all 3 of these. Now, simplifying these fractions, just canceling a factor of 2 from numerator and denominator. Of course, a calculator is a nice thing to have in this situation. We could certainly use that. But canceling 2 from 18, we get 9. Canceling 2 from 38, we have 19. Each of these fractions is now 9 over 19. So multiply all these together. This will be 729 divided by, again, a calculator comes in handy, 6,859. So there's our probability there. And for independent events. Now, what happens if the events are dependent, yet they're linked by an and? So 2 events are dependent if the occurrence of one of them has an effect on the probability of the other one. All right, so it's kind of hard to imagine for now, based on the examples we've seen, but we'll see in this example how this will make pretty clear sense. What's the formula? The formula is probability of A and B is the probability of A times the probability of B with a little bit of an addition here, given that A has occurred. So the probability of B given that A occurred. All right? So we have to adjust the probability of B based on the fact that A has occurred. Okay, so let's see what kind of occasion in which that might arise. So down below, we have 20 chocolate-covered candies in a box. They're all shaped exactly alike. 5 of them are chocolate-covered cherries. We're going to select 3 candies at random, not knowing which is which, and ask what's the probability that all 3 are chocolate-covered cherries. Okay, so the probability that the first one is a cherry and the second one, right, if all 3 are going to be chocolate-covered cherries, we're going to think of the word and when we see all. All outcomes have to satisfy this event. Okay, so all 3 in a row. First one's cherry, second one's cherry, and the third one's a cherry. So let's do this. We know we're going to split it up as a product. So this I'll write a little line underneath to help us with that. The probability that the first one's a cherry, the probability that the second one is a cherry, and the probability that the third one is a cherry. So the probability that the first one is a chocolate-covered cherry, well, there are 5 chocolate-covered cherries in the box and 20 candies total. So we have 5 out of 20. And we'll multiply that by the probability that the second one is a chocolate-covered cherry, given that the first was a chocolate-covered cherry. Okay, well, now we've already used one of these 5 chocolate-covered cherries. One is gone. It's been removed from the box. We're not going to put it back. We're going to eat it. All right, so we've got 4 chocolate-covered cherries left. We've removed 1 candy from the total 20 candies, so this is 4 out of 19. Third, okay, moving on to select the third one, also a chocolate-covered cherry, just like the rest of them. We we realize there are only 3 chocolate-covered cherries, given that the first and second were chocolate-covered cherries. Right? Given first, second are cherries. So we'll have 3 left out of the 18 total left. And so here's our probability calculation. We have 5 out of 20 times 4 out of 19 times 3 out of 18. When we cancel common factors and multiply these fractions together, we should come out to 1 over 114. And that's a little bit under 1%. If you're looking at a decimal, or a little bit below 0.01. Right, so that's our dependent event. Usually it's we're sampling something without replacing, or it's very obvious that from one stage to the next, the probability in the situation is actually changing, and we can't just use the same probability times itself. So those are the AND events. Let's see the OR events. So when we connect 2 events with the word OR, we form a larger event. And let's go to the formula once again. So if A and B are 2 events and they're mutually exclusive, we'll talk about that in a moment, then the probability of A or B is the probability of A plus the probability of B. So for OR, it's a sum. For AND, we multiply. Or add and multiply. Okay? So if A and B are mutually exclusive, that's the one thing we need to be sure of when we use this formula. What does that mean? Well, if A and B, if it's impossible for events A and B to occur simultaneously, then the events are said to be mutually exclusive. In other words, A and B have no outcomes in common. So A and B have no outcomes in common. That is key. All right, that's by all our definitions, the easiest way to see this. Anyway, let's look at the example below now. We're dealt 1 card from a 52 card deck. Okay, if you're not familiar with a 52 card deck, just Google 52 card deck of playing cards, and you should get a good idea of what's going on there. So they're asking, what's the probability of being dealt a king or an ace? Okay, so we'll say the probability of being dealt a king or an ace, and that's equal to, well, it's an OR probability, so we know that we'll split it as the sum. I'll go ahead and write it down, and then we'll double check to make sure that it's okay for us to do that. We'll think through before we finish the problem. Okay, king or an ace. Well, the thing we have to ask ourselves, is it possible for this event and this event to overlap, to happen in the same card, in the same single dealing of a card? No, because no one card is a king and an ace. So it's either a king or an ace. So we know that these are mutually exclusive events. They can't occur at the same time for being dealt 1 card. Now the probability of a king, there's 4 kings in a deck of 52 cards. There are 4 aces in a deck of 52 cards. So each of their probabilities is 4 out of 52. We can add those numerators over the common denominator, cancel the common factor of 4, and we have 2 out of 13. Good. So that is our first OR probability calculation. Now next up, down below, we roll a single 6-sided die. What is the probability of rolling a 1 or a 6? Okay, and a single 6-sided die, a 1 or a 6. Now this one could be counted up with just the sample space of rolling a 6-sided die. But just to demonstrate that the rule works and to sort of practice it in an easy way, this is a good example to think through. So 1 or a 6 on a single roll of a 6-sided die. So since it's an OR, we'll split it up as the probability of a 1 showing up plus the probability of a 6. OR is add. Okay. Now what's the probability that we roll a 1 on a 6-sided die? Well, there's 1 1 on a 6-sided die of the 6 faces that it could land on, so 1 out of 6. Plus, there's 1 6 on a 6-sided die, so there's 1 chance for a 6 out of the 6 faces on the die. 1 6 plus 1 6, there's a common denominator. The numerators add to 2 over 6, and we can simplify that to 1/3. So the probability of rolling a 1 or a 6 is 1/3, or 2 out of 6. We could see that with the sample space again, but it's nice to see it in this OR structure and verify that it's the same answer we would have gotten the other way. So those are mutually exclusive OR events. What happens when events aren't mutually exclusive? Well, they have some kind of overlap. A and B have outcomes in common. It's possible for A and B to both occur. So we'll see that in the examples. First, let's see what to do for the formula. It's a little bit easier, this formula. The probability of A or B for non-mutually exclusive events is the probability of A plus B, just as before, with one more requirement of minus the probability of A and B. Well, if we need to be really savvy, we know how to find the probability of A and B. We've already seen that, so we could use that formula if needed. Most problems are easier than that. You won't have to go into that formula. But let's see in the examples below. So, we're dealt one card from a 52 card deck. Find the probability that you are dealt a 5 or a red card. This is part A. So again, look at that 52 card deck online if you need to. Red cards, black cards, aces, hearts, diamonds, spades, clubs, or suits. Half the cards are red, half the cards are black. The cards are numbered from ace through king, so there are 13 in each suit. You can see all of that in a photo of the 52 card, or an image of the 52 cards in a playing card deck. No jokers. No jokers in these. So, what's the probability that we're dealt a 5 or a red card in a single card? So the probability of a 5 or a red card. So it's an OR. We pick up on that right away. OR problems are usually easy to spot because the word OR is in them. And problems don't always have an and in them. The probability of 5 plus the probability of a red. Right? So the probability of a 5 is, well, before we start to carry out each calculation, we have to ask ourselves, are these events mutually exclusive? Can you get a 5 card and a red card? Yeah, there are 2 red 5s in the deck, 5 of diamonds, 5 of hearts. So these are not mutually exclusive events. A 5 or a red, each of those is an event, but they do have some overlap. So we need to subtract the probability that the card is 5 and red. It's kind of funny possibly, but 5 and red is just a red 5. Anyway, the probability that we're dealt a 5 is 4 out of 52, 4 5s in the deck out of the 52 cards total, plus the 4 out of 50, plus 26 red cards out of 52, minus there are 2 red 5s out of 52. We just don't want to double count those two red 5s, because 2 red 5s were counted in here and in here. They should be counted once, but not twice. That's why we subtract this 2 right here out of 52. So all told, this comes out to 28 over 52. When we reduce it, we'll get 7 out of 13 by canceling a common factor of 4. Good. Now next up, what's the probability that we're dealt a heart or an ace in a single card? So let's see, the probability that it is a heart or an ace. Okay, just using an A for ace now. Okay, heart or ace. So or probabilities, we'll just start with that. The probability that it's a heart plus the probability that it's an ace. And we'll throw in minus the probability that it is a heart and an ace. Okay? So the probability that it's a heart. Well, a heart is a suit. There are 13 hearts. There are 13 cards in any suit. So there are 13 hearts in the deck, over 52 cards total. Or we could be dealt an ace. It's another way to satisfy heart or ace. There are 4 aces in the deck out of 52. And then we have to subtract the probability that we're dealt a heart and an ace in that single card. In other words, that we're dealt the ace of hearts. There's 1 ace of hearts. So there's 1 out of 52. Remember that 1 ace of hearts was counted in here as the part of the 4 aces, and in here as part of the 13 hearts. So we need to get rid of 1 extra copy, and that's why that subtraction's there. So we have 16 out of 52, and this reduces to 4 out of 13 once we cancel common factors of 4. So 2 mutually exclusive events. Let's look at something with a bit more relative frequency, or that's a relative frequency problem. So a student is selected at random from a group of 150 students. We have our total, 150, in which 85 take a math class, 60 take an English class, and 50 take both an English class and a math class. What is the probability that the student selected takes math or English? So we're going to select one random student from this 150. We know how many take a math class, how many take an English class, and how many take both. So the probability of selecting a student that takes math or English, well, we see this situation. They're either in an English class or they're in a math class. Or they're in both, potentially. But we can split that or just simply, just like ace and hearts, as a plus, so we have probability of math plus the probability of English. And then minus the probability that the student is in both math and English. Okay, so the probability that a student's in math, well, there are 85 students in a math class out of the 150 students total, plus there are 60 students in the English class out of 150 students total, and there are 50 students who take both a math class and an English class out of 150 total. So the numerators can all combine, adding and subtracting over that common denominator of 150. And what we end up with is 95 over 150. And when we cancel common factors of 5, we'll have 19 out of 30. And that's a reasonable place to leave that simplified fraction. So they can be used, these and or techniques can be used for relative frequency probabilities just as well as theoretical probabilities like we did previously. So that's it for this video. I hope these problems go well. Practice these. In the next one, we'll look at least once probabilities, and that will finish the 7B video lectures.